In this video, I'll explain the proof of Theorem 2 for the paper Uniqueness of DRS as the two-operator resolvent-splitting and Impossibility of three-operator resolvent-splitting. Furthermore, I'll present a corollary that directly follows from Theorem 1 and Theorem 2. This corollary establishes DRS as the unique two-operator resolvent-splitting, and that is the conclusion promised by the first part of the title. Before we move on to Theorem 2, let's review Theorem 1. Theorem 1 states that up to equivalence, T, S is a frugal resolvent-splitting without lifting for the problem class 2-op RD if and only if it is of this form. Note that this theorem states nothing about convergence. Convergence will be the focus of the next theorem. Theorem 2 states that the splitting of Theorem 1 converges unconditionally if and only if alpha is equal to beta and theta is between 0 and 2. This result assumes that the underlying dimension of the Euclidean space is bigger than or equal to 2, and therefore this theorem does not apply to monotone operators that map from R to R. Let's formally define unconditional convergence. We say T, S converges unconditionally for the problem class 2-op RD if the fixed point iteration converges to a limit and the solution mapping applied to the limit is a solution to the monotone inclusion problem for any starting point Z0 and any pair of maximal monotone operators A, B, provided that a solution exists. To clarify, T to the power K is T composed K times with the operators A and B fixed. We say the convergence is unconditional because there are no conditions on the monotone operators A and B or the starting point Z0. However, we are assuming that a solution exists. The notion of unconditional convergence is unrelated to weak and strong convergence. In infinite dimensional spaces, we would require the convergence to hold weakly, but weak and strong convergence coincide in finite dimensions. We avoid infinite dimensional spaces because defining the notion of lifting would become awkward in infinite dimensional spaces. Now let's start the proof. When alpha is equal to beta, the splitting of Theorem 1 reduces to the setup of DRS. It is well known that DRS converges for all maximal monotone operators A and B if and only if theta is between 0 and 2. Now assume alpha is not equal to beta. For the moment, consider the case D equals 2. Consider the monotone inclusion problem of this form where A and B are defined in this manner. Since alpha is not equal to beta, it is easy to see that A plus B is not equal to 0, and that 0 is the unique solution to this monotone inclusion problem. With basic algebra, which I will not go through, we can verify that the output of the fixed point mapping is of this form. With basic computation, we can show that the eigenvalues of this matrix is of this form, and we can show that this quantity is strictly bigger than 1. Therefore, for any starting point, the fixed point iteration diverges in the sense that the iterates go to infinity and that the output of the solution mapping go to infinity. When the underlying dimension is strictly bigger than 2, we arrive at the same conclusion by considering the monotone operators defined by these matrices. These matrices provide the same counterexample embedded into D dimensions. Now let me state a corollary that follows from Theorem 1 and Theorem 2. Up to equivalence, Douglas-Rachford splitting, which is a collection parameterized by alpha, theta, and eta, is the collection of all frugal, unconditionally convergent resolvent splittings without lifting for the problem class 2-op RD when the underlying dimension D is bigger than or equal to 2. The proof immediately follows from Theorem 1 and Theorem 2. A frugal resolvent splitting without lifting must be equivalent to a splitting of the form of Theorem 1. If this resolvent splitting is furthermore unconditionally convergent, then by Theorem 2 we have alpha equals beta and theta between 0 and 2, and this case corresponds to DRS.